Hello everyone, my name is Diego Cepeda and I'll be talking about PHPRX, an efficient hash table for persistent memory. So let's begin with our motivation. Persistent memory is here since 2019, offering the capacity and persistence of secondary storage and offering byte addressability, which allows developers to implement recoverable in-memory data structures. Still, ensuring persistence is not straightforward. Why? Well, cache remains volatile, hence we need to use flush instructions to ensure data is persisted. As well, we need to ensure that the stores are atomic, which is limited by an 8-byte aligned store. Before talking about our implementation, let's briefly describe some of the related work. We divide the related work into 3 approaches. The conversion approach, where a DRAM implementation is adapted to work with persistent memory, but at the same time it does not take into consideration the hardware characteristics of persistent memory. New designs, which offer fast recovery and data locality, while being complex and performing all their stores in persistent memory, which is expensive. And hybrid designs, which try to reduce the number of stores to persistent memory to increase performance while sacrificing some of the recovery time that will be spent rebuilding the volatile counterpart of these structures. For our implementation, we combine the conversion and hybrid approach. So let's take a look at the base of our design. Our implementation is based from the log-based version of CLHT, which is a 3-layer data structure comprised of a root item, a hash table item, and bucket items. For our allocation, 2 memory map files are used. The first memory map file is used to store static items. We will call this file the entry point item. This contains all the necessary data needed for recovery and is the first item the data structure will access after a crash or power failure. A second memory map file will be used for dynamic allocation. For the static file, we set the root item and a set of hash table items as part of the entry point item. We decided to statically allocate hash table items since arguably during execution we only need 2 instances of this item being present, one pointing to the current table and one pointing to the new table. Then we can reuse these statically allocated hash table items similarly to that of a circular buffer and at the same time reduce the complexity of dynamic allocation. For dynamic allocation, the notion of a chunk is introduced. A chunk is comprised of a contiguous array of bucket items and individually allocated overflow bucket items. A chunk will change its size during runtime as we start placing overflow buckets and will be locked when a full table resize is triggered. The memory map file for dynamic allocation is set to a size of 512 megabytes and can be extended if more space is required for dynamic allocation. Now, let's take an overview of PHPRX. As seen in the image, this is a hybrid implementation where the access item current is used to store the computed pointers from the offsets stored in persistent memory. The access item resize is used to store the pointers of the new table while the full table resize is performed. And we also have an array of volatile logs, which we use for concurrency control. Now let's talk about the parallel resize. The basic idea behind the resize mechanism is to have a small number of threads initializing the volatile logs and a large number of threads rehashing the hash table. In this implementation, there can be up to 8 threads helping on DRAM and 32 threads helping on PMEM. To designate reserved portions of the volatile log array and the table, we introduce the notion of a section. This section represents slots where a single thread can perform either the initialization or the rehash operation. Now let's talk about recovery. For recovery, we use a single-threaded approach, which consists of scanning the whole data structure in search of inconsistent states. To determine the consistent states that can remain in our data structure, all the operations which perform more than one 8-byte aligned store need to be analyzed. In our case, there is where the insert, delete, and full table resize operations. Now let's go to our evaluation. We used an Intel Xenon Gold server with Intel obtained persistent memory. We used the YCSB benchmark, which consists of a load phase and a workload phase. The load phase creates the hash table and inserts 64 million key value pairs. The workload phase is used to measure the performance of insert and search workloads and consists of 64 million operations. We compare our implementation to Dash, which is one of the latest persistent memory hash table implementations that has outperformed several other approaches. The first results are exclusively for our implementation, and it just shows that by placing logs in volatile memory, the implementation had 10% fewer cache misses, increasing performance. Now, for the write-heavy workloads, PHPRX benefits greatly from the low allocation overhead and the use of volatile logs, being up to 50% faster on the 50/50 workload and 30% faster in the 80/20 workload. In contrast, the difference in performance between PHPRX and Dash is smaller in read-dominated workloads, being up to 18% faster in the 100 workload and 20% faster in the 95/5 workload. The performance advantage of PHPRX comes from the simplicity of the implementation, since Dash uses several techniques for load balancing, and it might mean that searches might need to probe more than one bucket. Finally, we have here the results of the load phase. The main advantage we have during the load phase, in contrast with Dash, it's the low initialization time, that is around of 3 milliseconds. PHPRX only needs to create a 512 megabyte memory map file upon its first initialization, and then this file is resized dynamically as needed during runtime. On the other hand, Dash needs to map a large enough memory map file to contain the entire data structure, as it does not expand the file after initialization. For our experiment, the initial file size for Dash needed to be 8 gigabytes, which was a value determined by trial and error to suffice the workloads used on our experiments. So finally, in conclusion, we can say that the incremental expansion of memory map files can considerably reduce the initialization time, that it is crucial to take into consideration the access granularity of these devices when designing persistent memory data structures, and that allocation for persistent memory is expensive. Thank you everybody for your time. Have a great day.